So when I set out to give this course, we all talked in our first Flipgrid about what our goals were. And for me, it was just to really understand the contemporary landscape for astronomy today. And really, I wanted to learn a lot of things, and I wanted to learn where we were at since I studied a lot of these materials in college and grad school. And it's come a long way. It's one of those disciplines that's just constantly on the move, which is really exciting. And yeah, I've learned a ton. So I wanted to just go over a few of the things that I think are most exciting right now, some of the real mysteries, the holes in our understanding that your generation is going to crank on if you end up working in science, or even if you don't, you'll be paying attention to them as they surface in the news. And so I want to talk about a few of those, and then I want to close down with a little discussion of the concept of cosmology, because next semester, I hope all of you will sign up for the course if you're able to. I think it's going to be even better than this semester because the topics in some sense are, because the whole concept of cosmology is a deeply human enterprise. It's really about ascribing order to the chaos of the universe. And that's a project that's been going on long before history, certainly maybe tens, maybe even hundreds of thousands of years. And some of these stories that we have told ourselves, and the ones that we are still assigning evidence to, are essentially ancient narratives. And it's going to be really, really fun to explore those. We're also going to talk about how the sun works, which is a really unfortunate part of the way this is organized, is we didn't get to talk about the sun at all, which is sort of the most important body in our solar system, in a sense. I think that everything would get along fine without most of the planets, but probably not without the sun. So, and the sun is so complex, and it's so poorly understood, right? You can't send a spaceship there. We have sent one probe to the very far outer reaches of it, right? But it's very, very difficult piece of material to study. And so the theories for how the sun works are very young, actually. They've all been developed within the last, I'd say, since the mid-20th century for the most part, and we haven't significantly updated them. And there's a lot of pieces on the move with that too, the way that we understand the sun. And the way that we understand the sun ultimately feeds back into the way that we interpret cosmology too, which is really fascinating. So if we change our understanding about the sun, we're going to change our cosmology. And so it's kind of this, it's like the main character of any story of astronomy is our own sun. So we're going to spend several weeks talking about that and going over the history of how we've come to understand the sun and some of the methods. And yeah, the sun is just absolutely astounding. So we'll do the sun in depth, and then we'll get into all of the favorite spooky topics. We'll talk about the Big Bang. We'll talk about black holes, all sorts of other far-out ideas, and investigate why people have come to believe in a lot of these things that sound like science fiction, and how that happens. So without getting too deep into that, I do want to plug that course because I think that it's going to be super awesome. So, like I said, let's go through some of my favorite mysteries. And then I'm going to bridge over. I want to read you one somewhat substantial passage from the native science book, which I think is a good introduction into the concept of cosmology. Because it's really important when we think about understanding the universe that we don't get completely locked into this materialistic perspective of how things work. Science can do a lot of things for us. It can tell us how things work, but it can't really tell us how we should behave, right? And a lot of the purposes of cosmologies historically have been to give people a sense of purpose in a universe such that they can actually aim towards a behavior that is commensurate with a better life for everybody on Earth. And so a lot of that narrative has been traditionally corrupted by religions. There's always a priest class that's willing to insert itself into the dialogue and get in the way of that. But the myths have transcended all of that time, and it's it makes them much more valuable than simple stories that people have told themselves to entertain themselves over the years. And I think the fact that our cosmology today, even our scientific cosmology, very much reflects a deeply ancient cosmology is indicative of the fact that we can't shake the truth behind these. And so I want to read you a Lakota creation story towards the end of this lecture. And I want you to think about it as something that's not just a silly story, but something that perhaps is as true as a scientific story, in that it doesn't address the material aspects, but the metaphor and analogy speak to something that's deeply real, perhaps more real than some mechanistic understanding that we have, in that those narratives have persisted for thousands and thousands of years because they're useful. You know, people have rediscovered them in different civilizations that had no contact with one another. And so that's really, really important, not for us, especially as we move into this deep modern future where we have control over every aspect of our lives and everybody can essentially come up with, we have the freedom to choose our own ideas about how we see the world, our own senses of spirituality and religion and all of these. It's very important not to completely disregard the past as we open up ourselves to the chaos of all of those choices. So, all right, let's kick it off. So, if you take one thing away from planetary science, I want you to, well, I think is one of the most important mysteries is magnetic fields and the cores of planets, right? This is another thing that's sort of like the sun, where we can see some stuff on the outside. We can see planets that do have magnetic fields. They're obviously quite limited, but we can't really see inside of the planets. In fact, when we go to them and we go near them, we can, shine light. We can look at seismic reflections inside of them if we get close enough, but it's very difficult, other than looking at the mass and radius to pull out the density to make decisions about what's happening inside of them. So, Jupiter and Saturn have really big and perfectly aligned magnetic fields. And some place like Mercury has a really tiny magnetic field, and it's not entirely clear why that is, especially when you think about Venus, which is so similar to Earth. It has all of this geological activity. It seems to have all of the right densities necessary to have a nice core that's liquid. It seems to have all of the proper templates to have convection cells just like the Earth, but yet there's no magnetic field for Venus. And so this should really, well, it does certainly give everyone pause for concern about the way that we understand how these are generated. Maybe this mechanism that we talked about is completely wrong. It's totally possible that we don't understand anything about how magnetic fields are generated. Now that's unlikely. It probably is correct by degrees, but needs to be integrated with new information. So hopefully, as we reach out and start to explore Venus, we'll get a better sense of what's going on. It's very hot. All of our probes have lived about 30 minutes when they hit Venus. So there's a lot to be done. And we talked a bit about how maybe we could park something in the clouds and study it that way, which is promising. Uranus and Neptune are really strange. So their fields are not in line with the direction of the rotation of those planets, which is really strange. Uranus, the poles are completely out of plane with its orbit, which is very strange. And this isn't understood why this is the case. And it's almost certainly going to feed back into our story of the solar system and how it formed, which is another point that I'm going to get to in a second. But these are really, really exciting moments. These are really exciting topics for future scientists, if any of you should choose to take on that burden. is anybody in this room, this is obviously a course that's probably aimed mostly at non-majors. Is anybody playing with a career in science? A little bit there, Theodore? No? All right, fair enough. I do think, all right, so that's a totally different aspect. For those of you who are considering it, there's a lot of options here, right? For those of you who aren't, you should hopefully come away from this understanding how much our scientific, well, you probably understood this before you even took this class, but the way that we understand science really feeds back into the way that we live our lives on this planet, right? The decisions that we make with the technology that's developed. And so I hope all of you will at least walk away and engage a bit more with those ideas, you know? I want you to understand that science is a human endeavor, and just because you're not a scientist doesn't mean you can't have ideas about it and discuss those, right? So stay involved, stay on top of it. You know, the cores are really interesting too, because of course they feed back into this. The gas giants, we suspect, have cores because of this magnetic field business, but it's definitely a matter of constant debate, especially when we talk about the evolution of these cores and the icy bodies like Neptune and Uranus. You know, it's really striking how similar their cores are to some of the moons that we see in the solar system, and the idea that a lot of the asteroids that we're finding in the asteroid belt seem to have composition that suggests that they may have been the cores of some planets that got blasted away in the early years of the solar system, or maybe a different solar system altogether. So the cores are going to be, studying those bodies is going to teach us a lot about how planets evolve and perhaps how magnetic fields are stabilized. It strikes me that if we're going to do things like rescue planets from the dead, you know, this is a huge project in the minds of many NASA types, is terraforming other planets, terraforming moons. And a huge step is going to be the question of whether we can restore some magnetic field to these bodies, because without it, it's going to be a really treacherous place to live. And the travel is, of course, extremely difficult. So, yeah, that's a huge topic, something to think about. There's also, I mentioned this too, the planets don't, for the most part, one thing that's really, really interesting is that all the planets do orbit in the same direction. However, they have different tilts. Venus is rotating the wrong direction, which is really strange. And all of these anomalies always suggest that something discrete and interesting happened. And so when you read about a planet that's not behaving like everyone else, you need to think about some sort of event that couldn't have been, that doesn't really fit into the nice formation model that we started off with when I was a kid, and which has evolved significantly since then. And we'll talk in a second just about how the narratives for the formation have changed. And we've talked about it already in this class, but you know, several of the moon systems, especially in the outer planets, are orbiting retrograde, which to us indicates that they've been captured at some point. We're not entirely sure how you would capture a moon and it would be stabilized into a perfect near circular orbit so nicely. And when we think about the models for the formation of the solar system, generally the reason that's given for why everything must have formed in place is because its orbit is so stable. But that doesn't seem to be like a solid argument if you see moons that are orbiting the wrong direction and they have stable orbits too. The question is, the most solid piece of evidence I think that we have that the solar system formed all at once is that everything is going in the same direction, in the same plane. Now, it may be the case that during the formation process, there was another star, things got scooped up, there was leftover planets maybe out in the region that got swept into the mix. Maybe even our biggest gas giant, Jupiter, is a leftover piece of that formation. Maybe it was a binary system originally, and two stars were coalescing, and one of them took all of the material up and became the sun, and the other one was left over, was Jupiter. Maybe our binary sister got scooped into a completely different solar system altogether. So really cool mysteries there. There's a lot of asteroids that also have retrograde orbits, which is interesting. People think maybe they're burnt out comets or something like that. Another really interesting series of mysteries is about Mars, which is something I think that will really illuminate more as you guys move into the future and see the headlines, right? I just saw this headline, I think the day before, maybe this was Monday, which is pretty cool, but that the planetary scientists working on the Mars project have recently discovered that there are some not quite dead magma chambers on Mars, which is really interesting. Mars indicates that it did maybe have a magnetic field in the past, and it can probably give us some idea of where our planet is heading. And maybe there's ways to mitigate that in the future as well. But it looks like, whereas we once thought Mars was completely cold and dead, and I think probably when I showed you the pictures of the interior of Mars, there was very little hope that there was anything bubbling underground in the way of hot material. And it seems to be that just this week, that paradigm has completely shifted, right? That's how fast things are changing in this science, which is pretty awesome. Mars, this helps us understand it has one of the biggest, I think, the biggest the biggest volcano in the solar system. And it's also the highest known mountain of any planet. Mars also has a number of really bizarre features. So this one we talked about very briefly. This thing is crazy looking, this gash on the side of Mars, which people have had a really hard time explaining. It doesn't seem like it's effluvial. It doesn't have these water inlets and outlets, so like our Grand Canyon. It's also way bigger than our Grand Canyon, but and not bigger than our oceanic trench. But there's something very bizarre about this feature. So I expect to see wild explanations for this appear in the future. The best thing I think that people are revolving around is that it's a tectonic feature, like our oceanic trenches. But I don't know. It's you've got to admit this is a weird looking feature that we don't really see anything like on Earth, and so I expect that the explanation as that unfolds is going to change wildly too. Another question about Mars is, was there water on it in the past? Flowing water. And it seems like every time we find something that points to a flow, there's always detractors saying that no, it's just some sort of dune activity, or it's some sort of sublimation activity, like there's something that evaporated or made these features as it was a dry feature, right? Because rolling dust can actually look a lot, in terms of weathering rocks, can look a lot like water. And so the question is really, how close of a template is Mars to us? Does it represent a very quickly evolving version of Earth, or is it a completely different story that we haven't integrated yet? And I think most people would love to think that Mars is something that we can take as a record of our own past. And I think just in general, Mars is quite the sandbox for the concept of life on Earth, right? There's still considerable debate about whether we have detected features of life on Mars. There are NASA emeritus scientists that still to this day swear that the original lander detected life in the form of this labeled release experiment, which I talked about when we did Mars, which was really looking at how molecules reacted with other molecules on Mars with respect to controls. And there's several gentlemen who insist that was a completely positive result. And the new landers don't have the same equipment. I think in the future they will. But this Mars really opens up that whole topic of, what are the requirements for life? If we find something there, will it indicate that it's just come from Earth? Did we contaminate it somehow? It's going to be a difficult question to answer. And of course, the search for life in the solar system is really an old discussion. So some of the original Enlightenment thinkers were absolutely convinced that life existed in the solar system. Life occurred in the solar system. I don't know if I mentioned this, but Nicholas of Cusa, who was a philosopher in the 1400s, originally speculated that the Earth was a brilliant star, just like any of the other visible in space, which was really prescient. This is, of course, long before a century or two before telescopes. And he was absolutely convinced that these extraterrestrial bodies, these other stars, they of course thought of all of the bodies as stars at the time, inhabited some sort of intelligent creatures and plants and animals and all of this. And Descartes seconded that, writing that we would basically never be able to prove it, but that almost certainly there were intelligent creatures out there. And it's really interesting how these people thought of all of these planets as stars and didn't make the distinction, because one of the first things the modern astronomers did was make distinctions between the planets and stars. However, when you start thinking about the concept of brown dwarfs being essentially failed stars, and Jupiter essentially being of a similar composition to a star, and you start talking about the evolution of Neptunes into super-Earths, and you really get to this point where you realize these bodies do seem to be on a continuum to some extent. And of course, that's we're not at the point with our timelines that we can say with any certainty that these evolutions took place or didn't take place. All we can say is that it looks to be like there's a lot of parallels between the formation of these bodies. And so, excuse me, I think that's one of the really interesting pieces of this whole course, is that a lot of our ancient ideas resurface later. When I think about, I already talked about our cosmologies and how, and we'll learn so much more about that next semester, but how similar they are to ideas that were thousands and thousands of years old. When we talk about the formation of the solar system in general, we can't help but think how little things have changed since Laplace and Kant essentially said, hey, all of this stuff formed out of a disk of material that coalesced, all of these bodies formed together. And we went through this whole series of ideas trying to explain how this could have happened. People initially, the modern contemporary rational astronomers of their day, particularly in the 20th century, they couldn't accept that this was the case because of the angular momentum problem, right? The sun is not spinning fast enough. All of the angular momentum is in the planets. And we know angular momentum must be conserved, right? Something's not going to stop spinning unless something stops it from spinning. And so the 20th century astronomers, they couldn't believe that the solar system would form like that altogether. And they tried on dozens of different theories, and they entertained them quite seriously throughout the 20th century. And at the end of the day, they couldn't do it. They didn't come up with a better idea. And so they came back to the 400-year-old theory that all of these bodies coalesced out of this protostar circumstellar disk, which is just a really interesting full circle for how knowledge can work sometimes. Sometimes the new ideas go through all of these changes before they come back to something that's very old and steady. And I have a feeling that that's probably behind the persistence of myths as well, because you can come up with new stories and new characters and you can modernize things, but at the end of the day, the features that are most true are going to be the ones that stick. And I think that's why you see this cycle of knowledge happening. And so I tend to think of our acquisition of knowledge as like a spiral, right? We go completely away from some idea, and then we don't quite come back to the exact same starting place. We move forward just a little bit, and the spiral kind of works its way upwards. And I think that's the best case scenario for science, is that we don't get ever completely in love with our own theories of how things work. We're always open to the possibility that there's something new, but also that there's something to be maintained from the past. I've talked a lot on this show about, I do this podcast with my wife, and we're constantly talking to people who have new theories of science. And it's taken us a while to get a good view of how this works, but because we talk to a lot of lunatics too, who have theories outside of right, outside of the academy, because we suspected that the lunatics actually have a few good ideas amongst all of their crazy ideas, which seems to be true actually. Almost every scientific breakthrough that's ever happened, Darwin's a great example, but almost everybody was treated like a complete moron, oftentimes throughout their entire lives before their theories were accepted. And I think there's a lot of that stuff floating around today, where people have 100 terrible ideas and one really brilliant one, and so you'll never hear about them. But we think a lot about why that's the case. And one thing that really strikes me as the difference between a scientist who's likely to have their theory accepted in their lifetime and one who will never is that the ones that know how to play with other people do really well. And the ones that have respect for the past and for the people that came before them, they have a much better shot too. And there's a lot of people on the fringes of science who, both in the academy and outside of the academy, who have this attitude that, they're struck by the amazement with their own discovery or revelation about how something works, to the extent that they think everyone else is completely wrong. They'll even say that. This is all wrong. This whole thing is wrong. Not only, I think, is that misguided assessment of the landscape, but I think that it's something akin to political suicide. The worst thing you can do if you have an idea that goes in the face of everybody else is tell them that they're completely wrong. Because, like I said, with this spiral of science, most people are never completely wrong. They're only missing a few little pieces that could help them integrate their old theory into something that's new. And so I think that the key for the scientists that actually are moving things forward and are able to gain, for lack of a better word, a consensus, like really integrate themselves into the consensus, right, is that they are able to look at the past and see how their ideas fit into it. And, oh, hey, if we just maybe thought about this a little bit differently, right, instead of saying people have no idea how the solar system formed, which it's like, actually, they have like a lot of ideas about how the solar system formed, and they have a lot of evidence for that. But maybe a few things could be tweaked. Maybe there's some migration. Maybe there's evolutionary processes going on. Maybe the planets spend some time in this form, like say as an icy giant, before they transform into something that looks like a super Earth, right? These are integrative ways of approaching change, and I feel sad for people who aren't able to bring their ideas into the world that way. And I think it's something you guys can take into your lives in general, right? Because you're always, no matter what you do, you're going to be working on teams, you're going to be working with other people, and people are going to have ideas that conflict with yours. And if you really want your idea to make its way in the world, you're going to have to find a way to integrate the people on your team, to integrate their perspectives in a way that's constructive. And I think it's actually the most important thing that you can remember going out into whatever your profession is or whatever you end up studying. The people are what matter the most. You can have the best idea in the world, and if you can't get along with people and you can't collaborate, no one will care. It really doesn't matter. Having a good idea is not enough. I mean, of course, you have to put in a ton of work too, and maybe that's the other side of the coin. But, you know, I just can't even tell you how many people I talk to who have really good ideas, but you'll never hear about them, and no one will ever hear about them until somebody who has the savvy to work and play with other people is able to rediscover that idea and bring it into play with other people. You know, the Oort cloud is also a huge mystery. All these things that the further we get away from our sun, the more difficult it is to make sense of what's happening out there, that the means of probing those objects is sort of beyond us. We have a couple of probes that are flying out into that region, but they were never designed to transmit information back, right? And so there's some talk of sending new probes out to the far reaches, but this Oort cloud region, if you can, you know, I don't know how easy it is for you to get a sense of scale here, but almost everything, you know, I think this is completely not drawn to scale, I'm sorry. But this Oort cloud is unbelievably far away. It's on the order of light years at its extent. The outer reach may be several light years away, which puts us essentially butting up exactly next to another system's Oort cloud. And I think that this is going to be a wonderful topic of development in the next century, because, you know, we'll get into this more in the cosmology class, but we have a really hard time explaining how galaxies stick together and how they rotate and what their dynamics are. And the cosmologists are at the point where they're inventing mysterious substances with matter properties to explain this. But I think that understanding how the Oort clouds interact frictionally with one another is going to go a long ways to understanding the rotation of the galaxies. And maybe I think we'll probably end up putting to rest a lot of the superstitious ideas that are quite popular right now. So Oort clouds are something to pay attention to. I mean, how many dwarf planets are even out there in the Kuiper belt? It's hard to keep track of them. How about beyond that? Are there full-on planets just swarming at the outer reaches of the Oort cloud? Maybe, because we have a hard time explaining why these comets come in periodically with such highly elliptical orbits, and that they can get gobbled up by a big body like Jupiter or swallowed by the sun, and still there's always more. It seems like something is happening out there that's destabilizing these bodies and sending them into you got to think about the power necessary to throw something at the sun from the outer reaches. It's substantial. So, you know, the last big topic that we've circled around this whole course is the formation of the solar system. Oops, sorry. And I talked a bit about that in terms of how similar it is to, how similar it is to the original conception. And, you know, one of the biggest changes that's happened in this, in addition to the evolutionary ideas, is the idea that migrations are a thing that happens, right? And originally, when a lot of these narratives were being constructed for the formation of the solar system and the planets, there was a huge rift culturally between the religionists and the rationalists. And this is not completely, this was a culture war, essentially, right? And of course, we have a culture war in our country right now, or in the global community right now. But I think as a result of this, the rationalists were so hyper-allergic to catastrophism, which was traditionally used to defend the Bible, that they were absolutely unwilling to entertain the idea that any sorts of big changes could have occurred without us knowing about them in the deep past. And it's a really interesting evolution now, because if we haven't been successful in explaining how it is that when we look out at other solar systems that are forming for the first time, I mean, this is in the last 20 years, maybe even the last 10 years, that we've really been able to see other solar systems in formation, and they don't look like that. They don't have all of the planets, they don't have a bunch of rocky planets in the interior with a bunch of gas giants in the exterior. In fact, the young solar systems seem to have a bunch of photo-evaporating gas giants in the interior. And that's wild, right? This is completely against the standard model. After people argued about it for 100 years intensely in the modern literature about the formation processes, they settled on a model that seems to be completely incompatible with the data that we're now getting from the Kepler probes and all these exoplanet studies. Like I said, the majority of these systems have big Jupiter-like things that are just getting cooked in the interior. And this is really rewriting our understanding of how planets form. And I think it's going to be a really exciting next century. So, you know, science is always this push and pull between not just the empirical evidence, but what the culture is ready for, what people are in the mindset of being able to handle at the moment. And that makes, you know, I think there's another really important thing to take away from this, which is that science is kind of like having a trial in court, right? You know, why do we even have trials, right? You walk in and there's a dead body and there's a guy with a gun in the corner, and you're like, well, who cares, right? Well, it's obvious what happened, right? And, you know, many people, particularly non-scientists, people in the political sphere, people in the major media sources, are very quick to treat science as if this is how it works. That we see something, and it's obvious what it means, and that's it. But the reality of the situation is that all you ever have in the process of science, and it really is a process, all you ever have is some body of evidence which is constantly increasing. You never walk up and get a story from something. You only have the little shreds of details about what's going on. And generally speaking, those details are subject to myriad interpretations. Now, of course, I'm not trying to say that some interpretations aren't better than others. Certainly they are, and that's what a trial is all about. Ultimately, the defense can sit there and argue all day long that, you know, this guy just happens to, you know, have a violent relationship with his wife and just happened to find this gun in the room and just happened to have his fingerprints on the gun. But ultimately, these theories speak for themselves in that they argue the facts with respect to their narrative more successfully than others. But still, there are wrongfully convicted people in this country, many of them. The advent of DNA technology exonerated hundreds of people who, it turns out, were literally, I mean, people have been executed for crimes that they could not have committed. And we found that out after the fact because DNA technology became a thing, right? In the 80s and 90s, we were finally able to look at some of these cases and say, there's no way this person was at the scene of the crime. In fact, it was a completely different person altogether. And we have to maintain that mindset with respect to science too. We're always going to be coming up with new pieces of evidence, and we have to not fall in love with our narratives to the extent that we're unable to look at them. Otherwise, we could be terribly misguided and make terrible decisions, because ultimately, people really do, even non-scientists like yourselves, who will go on and participate in business and politics and law, are ultimately going to be informed by the scientific landscape, right? Because we want to believe that our society is just and rational and capable of making the right decision. That means that we also have to be willing to consider that we're wrong a lot of the time, and that we have to be able to update our priors as we go. So the solar system is a wonderful example of that. I don't think there's a science class that we could teach that would better exemplify this paradigm. And I hope that's meaningful to all of you guys as we go forward. So, right now it seems like the solar system formation model has at least evolved past the catastrophism, uniformitarianism debate. People are forced to grapple with the idea that orbits do change, that planets do migrate. A month or so, several lectures, probably 6 or 8 lectures, are going to be about the sun. The sun is, if you think that the solar system is on the move, the sun is even more on the move in terms of our understanding. I thought I would just tease you with one little concept, but the atmosphere of the sun is way more hot than the surface of the sun. This is very, very bizarre. It, by many stretches of the mind, violates basic concepts of thermodynamic equilibrium. How do you have an oven that has air, which is at 1,000,000 degrees, but the oven itself is only at 1,000 degrees, right? This is weird. It's very weird. And so there's a number of ideas about how that works out. There's also a number of contentions about how that temperature is even measured in the first place. And so we'll really get into how we get temperatures and how much we can lean on them. Are they true temperatures, or are they the temperatures of the light? And is the temperature of the light actually tell us about the temperature of the body, or is it something, is there more processes involved in that? And so I'm really excited to explore the sun with you guys if you'll stick around for that. Any questions about any of this so far? Hanging in there? All right. So I think what I want to do now is switch over and talk about the cosmology and talk a bit about myth. And I want to read you a passage from Native Science, and it's a couple of pages. So sit back, relax, and as we go through this, I want you to really think about what I said at the beginning of class about how some of the narratives that we tell ourselves, they have a real truthful element to them despite all of the superstition. I want you to try to look past the superstition and think about how these processes play out on Earth. I mean, it's not insignificant that we've named all of the bodies in our solar system after gods, right? And you have to ask yourself, what is a god really, right? And I think that it's a lot more than a superstitious, spirit or something like that. Like, let's take Venus, for example, right? It's like, well, people named this, this was a central deity in their culture, Venus, and so they named one of the planets after it. And it seems like everybody's kind of done this to some extent, but why did they do this? Why Venus? What does Venus really mean? And it's like, there are these elements, and I think like Jung, the psychoanalyst from the mid-20th century, really nailed this when he said that essentially all of us are, of course, we have these complex personalities. No two of you are in any way identical. In fact, you're probably very dissimilar. But your personalities are an agglomeration of a lot of sub-personalities as well. And there's aspects of your personality which bubble up sometimes and sort of act without you even knowing, right? I mean, has anyone ever been angry before, right? It's very strange being angry because, in a sense, you act something out that has nothing to do with you, right? You can fly into a rage and then you recover from it and you're like, what was that? Why did I say all those mean things or whatever, right? It happens without you knowing. And I think this actually really nailed this when he said that essentially all of us are Of course, we have these complex personalities. No two of you are in any way identical. In fact, you're probably very dissimilar. But your personalities are an agglomeration of a lot of sub-personalities as well. And there's aspects of your personality which bubble up sometimes and sort of act without you even knowing, right? I mean, has anyone ever been angry before, right? It's very strange being angry because, in a sense, you act something out that has nothing to do with you, right? You can fly into a rage and then you recover from it and you're like, what was that? Why did I say all those mean things or whatever, right? It happens without you knowing. And I think this is the roots of the concept of gods in civilization. It's like there are these conserved features of all of our personalities that come out. They're in there, they're inside of us. We don't know that they're there, but they show up. And so, Mars is the god of rage, right? And this is inside of everyone. Venus, the god of love and passion. It's inside of, if any of you have ever been in love before, it's like, you don't know, it's like it's not you. Like you're doing things, you're checking your phone, you want that message from that person, you're acting in a way that's like dragging you around, right? It's like you have your personality and everything, but it doesn't matter. These things they're so foundational inside of us that to say that they're just silly superstitions, I think is a terrible mistake to make, because in some sense, those gods, as they would call it, that live within us are more important and more real and play out in more real ways than your rational direction of yourself, the one that, say brings you to class or helps you choose which classes you take or anything like that. Sure, you have control over those things, but there's things inside of you that have control over you as well. And the ancients realized this, and every single ancient culture realized this, and they embodied them in these things they called gods. To some extent, the evolution of gods from paganism into these monotheistic cultures was, I think, an attempt to integrate all of these and be like, this is too much to keep track of. We can't keep track of all of our different passions and the things that lead us around. If we subsume them into one deity, maybe it'll be easier to have some big ideal which we can look up to, right? Because we need those role models about how we should behave. Obviously, we don't want to behave in a wrathful fashion, right? And so the question becomes, how do we subvert that? What do we want to behave like? And I think that's why all of these cultures have trended towards this monotheistic idea of an ideal. Because you say, what does God mean? Well, it's probably something close to the best possible behavior for a person, right? And so these aren't just silly, backwoods, superstitious people that have come up with these. These aren't just cave people being morons or ancient superstitious people. These are really, really important, deeply human pieces of what we are, of the way we behave. So anyways, let's check out a story from the Lakota tribe from our own land here. And I'm going to read from Kahete. This is Native Science. If you haven't got this book, I highly recommend it. It's a great read. There are stories among indigenous people that suggest visitations by extraterrestrial beings, that the stars are their ancestors or carry the spirit of their ancestors, and that when people die, they become stars or go among the stars. For instance, the Milky Way is described by certain peoples as the land of people who have gone on. There are stories that people come to the earth for a certain period of time and then return to the heavens to become star beings. The following story is an example. A long time ago, two Lakota girls went out one night to watch the stars. One of the girls said she wished she could marry that one big, beautiful star. The other girl said she wished the same about another beautiful star. Suddenly, they were taken into the star world, and it was there that the two stars became their husbands. Later, the girls became pregnant. They are told that the star world was theirs, but they were warned not to dig any wild turnips. Eventually, one of the girls pulled a turnip from the ground. A hole in the star world opened, and the Lakota woman was able to look down and see the earth and her village. Because she became homesick and wanted to return to the earth, she braided turnips to make a rope. The braided rope she made did not quite reach, and she fell to her death, although her child was born. The meadowlark raised her son, since they too speak Lakota. The baby boy was named Fallen Star. Fallen Star reached manhood in days rather than years. He was very tall, and light was always around him. The meadowlark grew old and decided to take him to a Lakota band where he could settle. Fallen Star traveled from band to band. Everywhere he was recognized for being the protector and the bringer of light. A Lakota band was camped near Hamey Park in the Black Hills. Every day, a red eagle swooped down and stole a little girl who was carried away to the top of the mountain and killed. All of the warriors tried to kill the red eagle, but they failed. All Lakota people prayed for the help of Fallen Star. He arrived after 7 days, and after 7 girls had been killed. Fallen Star killed the red eagle and placed the spirits of the 7 girls in the sky as a constellation. The constellation is known as the Pleiades in the Western world. And in Lakota, Winsinakala Sakawin, the 7 little girls. Another constellation is called Nape, which means hand in Lakota. To locate this constellation, one must first find Orion. The Orion belt comprises the wrist, Regal, the pointer finger, and Eridanus, Beta, the pinky. The story related to this constellation begins long ago when Fallen Star told everyone that he planned to marry the daughter of a chief in the nearby village. She told Fallen Star that the thunder beings had taken her away from her father's arms. She agreed to marry Fallen Star if he could get the chief's arm back. Fallen Star went in search of the arm, and he obtained special powers as he traveled through different villages. Fallen Star obtained sinew, a wren feather, a swallow feather, a live coal, an eagle plume, and many words of power. All of these things helped Fallen Star change his shape and escape the thunder beings. As Fallen Star traveled, he was in the Black Hills. But at the same time, he was traveling through the star world. He visited 3 villages of star peoples, and it is said that his son would have come to visit the other 4. Finally, Fallen Star reached the Wankenya thunder beings. By changing into a wren and then into a man, he was able to outwit the thunder beings and the trickster. Fallen Star recovered the chief's arm, and using the other powers he was given, he was able to flee. Fallen Star gave the arm to the chief, married his daughter, and later they had a son. The purpose of this story is to provide certain teachings. The chief represents selfishness for wanting his arm back. The thunder beings represent the annual disappearance of fertility, as well as the masculine power to refertilize. The arm symbolizes the earth. The power of life is lost and regained each year, but not without sacrifice. People who argue that such stories are wholly unscientific are begging the question of probabilities and possibilities. We know that life on Earth likely resulted from supernova activity, that is, a combination of certain types of electromagnetic radiation and bombardment by particles of matter. Thus, the notion that we are star people or stardust is quite reasonable. Currently, Western science says that yes, all life on Earth is stardust or comprised of the same elements as stars. Some of the necessary elements that made life possible on Earth could not have come from anywhere else but bombardment by asteroids. And of course, if it happened in this solar system, it most certainly happened in other solar systems. A belief in reincarnation is shared by many indigenous cultures around the world, such as the myth of Isis and Osiris among the peoples who built the pyramids in northern Africa. The ancient Pueblo myth about star people, that we return to the Milky Way after we die, is about reincarnation. According to a Chumash myth, the stars control everything on Earth, and it is said that the Earth is part of a great celestial being in the sky, Star Coyote on one side, and Old Man's Sun is on the other, and that the cosmic battle between creation and destruction is continuous. This is the fundamental concept in astrophysics. The universe cannot expand forever. There has to be an opposing force. Ancient indigenous peoples had very sophisticated understanding of how things worked, how things move, and how things happen in the universe. They use the coded form of mythology to try to convey their understanding because in some ways, understanding is beyond words. Incidentally, this is why physics is heavily dependent on mathematics. There are certain things that cannot be explained in words, and the relationship is not transparent unless you quantify it into some symbolic form. Indigenous peoples are doing the same thing in another form by coding their knowledge, understanding, and insights into the rituals that they perform, the mythologies that they've created, and the stories that they pass down. Now, I think this point about mathematics is absolutely killer. Numbers are not real. They're not materially significant. They're an abstraction, right? And the extent to which our civilization depends upon numbers and depends upon calculation and mathematics cannot be, it can't be overstated. We wouldn't have this building. We wouldn't have the car that I took to get here this morning. We certainly wouldn't have spaceships. And of course, we wouldn't have all of the terrible things that technology has brought us. We wouldn't have nuclear bombs and any of this, right? But our ability to abstract quantity and then to manipulate it in highly abstract ways is so real, right? And by the same token, I think that we have to consider that the other ways besides materialistic interpretations are equally real. They're abstractions, sure. They might seem a little silly on the surface, but there's real truth and utility and understanding and studying those ideas. And so, pick your, there's so much interesting literature, art, music, film out there. Fill your heads with the good stuff. Don't waste any time on things that don't actually give you a better sense of the truth of the universe. We have this rule in my house where if we start watching a movie and it just isn't hitting, we'll turn it off pretty much immediately, right? There's not enough time to waste on art and literature that isn't absolutely cutting at something. And you know when it's cutting at you because you lean into it, right? It's getting into something that's inside of you in a new way. And that's really, really important that we tune into it. All right, so I'm going to just crack open the concept of cosmology now, which really historically has addressed these bigger issues. And this is more or less a preview of next semester, but I want you guys to see it. This is a logarithmic representation of everything we can see in our own universe from where we're at. So essentially the things that are closest in this picture are the things we have the best view of. And as we move outward, to the absolute edge of our ability, we have a wonderful new telescope in orbit called the James Webb. And the images we're getting are magnificent. And one thing that's really beautiful about it is that it looks like the galaxies, these are individual galaxies in this last ring. It looks like the galaxies are organized into this incredible tendrils of web, which is just really astonishing. Because who knows what superstructures lie out there and on what timescales they operate. So cosmology, like we talked a bit about what cosmos versus chaos means, right? It's the attempt to impose order upon something that's otherwise quite intimidating and ill understood. So actually that word didn't show up until 1656. In something of an encyclopedia that was made at the time. And traditionally, cosmology has been a philosophical discipline. It wasn't even considered science until the mid-20th century. Some people would probably still argue that it's not a science, but we'll deal with that more next semester. But traditionally, cosmology has been concerned with basic questions like, what is the origin of the universe? What was the cause of the origin of the universe? Is existence mandatory? And what are the ultimate material pieces of the universe fundamentally? What are things made out of? And so that calls into questions about atomism and mechanism, That's where the science starts to come into play. What is the reason for the existence of the universe? Does the cosmos have a purpose? Does the existence of consciousness have a purpose? How did consciousness evolve? That's a really fun topic that we'll get into. And then, of course, physical cosmology is really asking, it's really a branch of physics and astrophysics that deals with the evolution of the universe, so how things change from the past to the future, which is really predicated on 3 pillars of evidence, which are, well, the fact that there's 3 of them is really interesting, in that there's not 150 or something like that. So there's 3 main pieces of evidence for our entire astrophysical cosmology, and we'll examine all of them in depth. But they essentially come down to the presence of the microwave background radiation, the distance recession velocity of the far-off galaxies. It seems like things that are further away from us appear perhaps to be moving away. And then the abundance of certain elements and so forth, and how we could talk about how those evolved over time. So all of these 3 things have essentially given us the cosmology that we have today. And there's a lot to say about each one of those, and a lot of uncertainties and interesting directions that could move. You know, the standard model also right now, it doesn't work without the construction of this stuff they call dark matter, which is going to be really fun to talk about. Because dark matter is, it's essentially, you know, the most unscientific concoction to hit the scientific table since phlogiston or miasma or something like that. You know, people used to think that disease was caused by bad air, which kind of doesn't turn out to be totally wrong. But it turns out we have infectious theories of disease now and so forth. Right now, we can't see the cause of a lot of the motions that we find when we turn our telescopes towards other star systems and towards the galaxy. It seems like they're being yanked around by materials that aren't there, and so we have reified that concept into a material called dark matter, which is undetectable, invisible, and it must be there because everything seems to be in motion because of it. You know, and so we're really at the bleeding edge of what's known when we start investigating star systems beyond our own, and particularly star systems in other galaxies altogether. It's worth reiterating that we thought the entire universe was contained within the Milky Way until about 75 years ago. That's really far out if you think about it, because that's only a few, I guess, 100 light years or something like that. Yeah. Maybe it's more. Maybe I'm off by a couple orders of magnitude. But the cosmos is billions of light years from what we can see. The universe is billions of light years across at this point, and increasing in size the further we can see. So this is going to be just an amazing chance to understand, to look into the real deep mysteries of what this place is and why we're here, and what it's been like in the past and what it'll be like in the future. And we'll really dig into those narratives, and I think it's going to be wonderful. And I really hope all of you will join me for that. Does anyone have any questions for over this whole course so far? I think I've covered about everything I meant to. I've learned a lot. I hope that you all did too. I really enjoyed your presentations for the most part. A lot of you put a tremendous amount of work into those, and I think everybody who has done the work in this class is going to do really well in it, so don't worry about that. Otherwise, I'm going to submit your final grades probably in the next day. I'm going down to LA to meet up with a few different scientists and see some friends and things like that. So I'm going to try to get everything done before the weekend. Please go tell your friends to all sign up for next semester. And I really appreciate you guys coming for this last course. I know it was cold and blustery morning, and you probably have other finals to worry about. I hope you guys have a wonderful break, and we'll see you guys again next semester. Thank you all.